Now remember, this is physics. Proceed with caution. Hi, this is Ben.
And Nick.
Now what we did in our initial trial run, using the sun, a magnifying glass, and some newspaper, we magnified the sun's rays using one point of the newspaper, and we created a flame. What I forgot was my dad has a plastic grill, not a metal one, so unfortunately we burned down the grill, thus...
Almost burning down the whole city of Wauwatosa.
Yes, Mom, thank you. We created physics.
In this experiment, we'll be using a convex lens, also called a converging lens. This type of lens uses light rays and converges them on one point, also called the focus point. All of the energy put through the lens is focused in one point. Let me demonstrate. See? The focus point on the cement is where all of the energy coming through the lens is concentrated. Outside, we use this magnifying glass to focus light rays from the sun. This is shown below in a more simplified manner. As light rays enter the prism, they refract, going from low to high index of refraction toward the normal. The ray then passes from high to low index of refraction as it refracts out of the prism, going away from the normal. This occurs on all of the rays, therefore the rays are focused coming out of this converging prism on one focus point. In a more complex sense, and more oblong lens, this converging lens, which is similar to this magnifying glass, focus the light right here.
Alright, now we're going to give you a little recreation of our near debacle before. So what we started out with was just, as we said before, a converging lens and a piece of paper to focus the light. So as you can see, if you come closer, that when we get a little point on there, we can start burning the paper. It might take a second. You see there's some flames coming off of there? And it starts to burn a hole. So now, if we continue to do this, it will start on fire and nearly burn things. But we're going to stop for now.
Now, you may be wondering how this works. Well, I have a diagram. Here's the sun, and the sun emits rays called UV rays in all directions across its surface. We are here, the planet Earth. Now, we are so far away from the sun that we receive only a small portion of the sun's rays. The rays that we receive from the sun can be considered parallel because the angle of difference between each of the rays is so minute that we consider them parallel. Which means these parallel rays produce enough power for us to magnify them, thus creating light. Now, you may be wondering, why does this not work with a light bulb? Well, like the sun, the light bulb emits rays. However, these are visible light rays, so they're not UV rays, but it emits rays in all directions across the surface. Now, when you magnify these rays, you still do get a focus point. However, these rays are not parallel because the distance between the light bulb and the magnifying glass is only a couple feet, unlike the distance between the Earth and the sun, which is millions and millions of miles. So, your focus image does not have enough power like the image that the sun did.
We also tried a very similar experiment with a mirror that we found. Due to its concavity, it also has a focus point, which can focus the UV rays on the paper, as you can kind of see here. But previously, we were able to do our magnifying glass experiment while the sun was at its peak, and now the sun's gone down a little bit, we're not able to burn the paper at this point. But because it's a concave lens and we have equations for the calculation of those focus points, we could show you mathematically approximately where it would burn.
Here is a ray diagram of a concave mirror. Using the P ray, which comes in parallel and goes out through the focal point, and the F ray, which comes in through the focal point and out parallel, we take an object that is in front of the focal point and get an object that is virtual, upright, and enlarged behind the concave mirror, which makes it virtual. Here's another diagram which simulates our observations outside. Here's the sun, and here's a concave mirror. The sun emits parallel UV rays, which means that when these rays hit the concave mirror, they come out to focus at a single point. This single point is where we saw the burning and the fire starting. When the sun emits these UV rays, they hit the concave mirror, forming first an angle of incidence, which is created with respect to the normal, and then it comes out through the reference angle, which is also the same angle, just on the opposite side of the normal. And the focus point right here is not the actual focus point like we know it to be F equals 1/2 R, but is the point where the rays are focused, or to say where the light is concentrated.
In order to numerically analyze our concave mirror, we had to take the whole situation into a different frame of reference. So, in order to create the concave dish we were looking at, you would imagine a plane having to pass through a sphere to create a rounded out shape. Thankfully, this system works mathematically almost exactly the same as passing a line, like this one, through a sphere or a circle in a Cartesian plane, which is defined by, as we all know, x squared plus y squared equals r squared. As you can see, this still creates the same rounded out shape, which has the same radius. We just can do away with the other dimension and still calculate correctly. So, using our centimeter ruler on the mirror, we found that the indent was about 0.5 centimeters, and the radius of the circle, the radius of the cross section we had, was 12.7 centimeters. Based on the knowledge that in our plane, this far edge of the circle would be negative r, we know that the x value here, the x component, is 0.5 minus r, because it comes out 0.5 centimeters. And then likewise, the y value is just the 12.7 that we measured. So, plugging this into our equation x squared plus y squared equals r squared, we can find that the radius is 161.54 centimeters, and thus the focal length would be about 80.77 centimeters, or using significant digits, 81 centimeters. However, because the sun's rays were not going straight through the primary axis of the mirror, we know that the sun wasn't exactly focused in that place. However, it still follows a general idea that we can find the focus and where the sun's rays should pass and their energies be collected.
I can ride my bike with no handlebars, no handlebars, no handlebars. I can ride my bike with no handlebars.
Revenge!
Physics.